Alright, we're going to start into circular motion problems now. We're going to do horizontal first, then we're going to do a little bit of a 2D horizontal. Like I said, not all trig is gone, and we're going to do vertical a little bit later. Before we get into circular motion problems though, there's just a few little things that we want to deal with. So, when we are dealing with centripetal force or the net force, we're only looking at forces that are in the same plane as the circle. So if the force is not in the plane of the circle, we don't care about it. So like for example, if I have a circle, if I have something moving in a circle like this, and if I have a force going this way, and maybe I have another force going that way, and then I have this force going down here, the only forces that contribute to the centripetal force are going to be those that are in the same plane as the circle. So this force is in the plane of the circle, it's going towards the center. This force is also in the plane of the circle. It may not be pointing towards the center of the circle, but it's still kind of in that flat plane. But this force right here, it's basically perpendicular to the circle. It's not in the plane of the circle, so that force would not contribute to FC. So I'm just going to say it does not contribute to FC. And I'll try and emphasize that point as we go through some of our examples. But yeah, you may need that force for something else, but if you're looking at centripetal force, you're only looking at forces in the plane of that circle, nothing else. Now, you may find, and this is similar to other problems we've done in kinematics and dynamics, if you're looking at one direction and you find you're kind of reaching a dead end, go to another direction instead. You may actually get a little bit, you may find it be more helpful, and then kind of link the two directions together. Always draw your free body diagrams, very important when we're dealing with force stuff. And then for positive convention, usually we're going to call towards the center of the circle as positive, and anything away from the center of the circle is negative. This is the easiest convention to deal with. Just because the centripetal force is always directed towards the center of the circle, we might as well just call that direction positive. It makes our life really easy. So for horizontal circular motion problems, there's really only two types of questions we can really ask you. It'd be something about like a car driving on a road and making a turn, or you may have like a tension in a string, something to that effect. So we have to think for a minute. Let's look at this car making a turn. And we can look at it in two ways. We can kind of look at a top-down view, or we can kind of look from a rear view. Now, if a car is going in a curve, there has to be a force to do that. In the absence of a net force, something's going to travel in a straight line. So if we didn't have a force acting on this car, it just want to go in a straight line, it's going to drive into those trees. As you probably know, driving into trees, not a good idea. So for that car to bend in a circle, it has to have a force that's directed towards the center of that circle. So something towards the center of that turn. If we have that force directed towards that center of the turn, the car is going to easily navigate, or the car will be able to make that curve and navigate around the turn. Another way of looking at this, so here's our car, here's this force towards the center, here's my normal force supporting the car, because the car still has a force of gravity that's going down, and then of course we have this normal force that's going up to support that. So this is where I was talking about in the plane of the circle. So the circle is kind of on the flat surface here. The only thing that contributes to the centripetal force is this force here. So this force of friction contributes to FC. The normal force and the force of gravity, they do not contribute to the centripetal force. So we shouldn't have Fn and Fg in our equation for centripetal force. In this case, the only force acting towards the center is Ff. Now, we may need Fn and Fg to determine Ff, but just to write our net force statement, the only force acting towards the center of the circle is our force of friction. Now, one of the things that always comes up is, if we're dealing with this, are we dealing with kinetic friction or are we dealing with static friction? So a lot of people want to say, and I would never blame them, the car is moving, it's got to be kinetic friction. It's a good idea to rationalize it that way, like I don't blame you, but it's not correct. We're actually dealing with static friction, because you want to keep in mind that when the car is navigating around the turn, we want the car to stay between the lines. We don't want it to slide to the left, nor do we want it to slide to the right. We just want it to stay in between the lines. So we want it fixed between the line and the edge here. So because we don't want it moving between this space, we're actually dealing with the force of static friction. At the end of the day, if you forget which friction is responsible, it won't matter, because you know the equation to determine the force of static friction versus the force of kinetic friction. You know it's the same thing. The same equation, just the only thing that changes is which coefficient you're using. But yeah, that's just something to be mindful of. So let's look at this. So we have a car. It happens to be rounding a turn. And then the car driver is going to feel the car begin to slip. So the car has a mass of 1,250 kilograms, and the radius of the turn is 35 meters. So what is the speed if the coefficient of friction between the car and the tires is, between the tires and the road is 0.57. So this is a coefficient of static friction, since we're dealing with static friction. So let's look at an FBD. And we're going to do two. So I'm going to do a top-down view. And we didn't really say where the car is turning, whether it's turning left or right. Let's just say it's a right turn. It doesn't actually matter. It doesn't change anything. So the car is going to turn right. So here's my road here. Here's my curve. Here's the center of that curve. So if I have a car that is going to turn to the right, in order for it to turn right, I'm going to need that force directed towards the center of the circle, because that force is going to be responsible for causing this car to curve. This is going to be our force of friction. In the top-down view, that's all we need, because it's like we're kind of standing above the car and looking at it. If we want to say look from a rear view, like if we were standing behind the car, like here's the car, we still have that force of friction going towards the center, and then we have that normal force going up and that force of gravity going down, and these are going to be balanced because they're equal. We don't have the car accelerating in that y direction. So that's just something to keep in mind. Which free body diagram helps you? Well, it really depends. They both have their uses. So let's look at the x direction. So in this x plane, this is where the circular motion's happening. So this is where we want to look at centripetal force. So the net force, or the centripetal force, acting in this x direction, or acting in the plane of the circle, the only thing acting in the plane of the circle is this force of friction. That's all we can put there. Now we have definitions. We know centripetal force is mv squared over r, and we know the force of friction is just going to be the coefficient of friction times the normal force, or the magnitude of the normal force rather. Now, we know m, we know v, or actually we're trying to determine v, we know r, we know mu, we don't know Fn. That's where this free body diagram is going to come into play. That's going to help us out. Now, I should say set my positive convention, so I'll say towards the center of the circle and up, we're going to call that positive. So in the y direction, we know that the net force in the y direction is just going to be this normal force plus this force due to gravity. Now, the car is not going to spontaneously accelerate in the y direction, so we know the net force in the y direction is going to be 0. So we know that Fn plus Fg is going to be 0, or we know that the normal force is just going to be the negative of the force of gravity. Let's see what we can do with this. Or we know that this is going to be negative m times g. We can plug this into our equation for centripetal force. We know that mv squared over r, this is equal to mu times the negative of mg. Well, the good news is the masses are going to cancel out. Mass becomes irrelevant. I have that negative. We're just going to bring it to the front. So we have this v squared over r equals negative mu times g. So for us, v is going to be negative mu times g times r. Now, we might start to have a little bit of a worry because we have that negative sign under there and mu and r are not negative. But keep in mind the direction of g. If we called up positive, g has to go in as negative 9.81. So that's going to take care of that negative there. So the speed on this thing is going to be the negative of 0.57 times negative 9.81 meters per second squared, and then times that radius of the turn of 35 meters. And then we're going to square root all that. So that's how we don't have to worry about that negative. But I can understand where people would get a little anxious. If you want to prevent some issues, or if you want to like soothe your anxiety on that a little bit, my recommendation would be to first calculate the value of Fn. So then just take your mass that we have, this 1250 kilos, multiply it by negative 9.81. You'll get an Fn positive value, plug it in here, and then you can solve. That would be my recommendation. But either way, what we're going to get for this is we're going to get that the speed of the car is 14 meters per second. Basically, what this is saying is that based on the conditions, that is essentially the maximum speed the car can travel around this turn before it starts to slip and slide off the road. So the main thing with these car problems is that the contributor to the centripetal force is only the force of friction. So the only other thing that we can really ask you is to deal with questions with centripetal force and tension. So let's have, and we are strictly speaking about horizontal circles. If you're in circular motion, we have to tell you whether it's horizontal or vertical unless context kind of makes it obvious. So like a car driving on a flat road, it's fairly obvious from context we're talking about horizontal motion. Now, with things that are on a string, we have to be very explicit. Is it horizontal or is it circular motion? So let's look. Is it horizontal or vertical circular motion? So we have a physics experiment. It's going to be performed by whirling a 10.2 gram rubber stopper on a 90 centimeter long string in a horizontal circle at a rate of 2.1 hertz. So let's find the magnitude of that force of tension. Okay, so I'm going to do a top-down view. So the top-down view for our FBD, here is our object. It's spinning in a circle. There's the center of the circle. So let's say my rubber stopper is located right about here. What that's telling me is that, here's my string. What that's telling me is that the only force that's going to be towards the center of this circle is this force of tension. Because the tension on that string, it's pulling on this stopper, it's pulling it towards the center of the circle. This is what is going to cause this rubber stopper to go in circular motion. So if I'm looking from this from the top down, the force of tension is the only thing I have to consider. So I can say that the centripetal force acting on this, or the magnitude of the centripetal force, it's just equal to the magnitude of the force of tension. So the force of tension's magnitude is just going to be that of Fc. Now we're given the frequency in hertz. We probably would like to convert that to period, so we're probably going to want to have a value for centripetal acceleration that involves period, because we know centripetal force is just m times centripetal acceleration. So that's where we're going to use this 4 pi squared r over t squared. Or you could write it as 4 pi squared rm over t squared. Or if you want to calculate other things, like you want to calculate period, then speed, and then use mv squared over r, that's fine too. So if we know the force of tension is the centripetal force, and we can have an equation for the centripetal force as this 4 pi squared rm over t squared, we need to find t, and we also have to deal with the mass because it's in grams, and we also have to deal with this 90 centimeters string. So there's actually a lot going on here. But first of all, we know period is 1 over frequency, so we're going to just deal with that one right off the bat. That's the easiest to deal with. So we're going to get about 0.476 seconds. The mass of 10.2 grams, for these equations to work with force, we need this in kilograms. So this has to go in as 0.0102 kilograms. Grams is not going to work. The last thing is people get a little confused about that 90 centimeter long string. you have to keep in mind, if we have this object, so like let's say I'm twirling this yo-yo, like, or whatever I happen to be twirling, this rubber stopper. So I'm holding onto the string. Here's the string. There's my rubber stopper. It's now going to go in a circle. It's going to go in a circle. That length of the rubber stopper, that 90 centimeters, this is my radius, because that string is starting at the center of the circle, my hand, and it's going all the way out to the edge of the circle. So we don't have to do anything with this number except make sure that it's in meters. So the radius of 90 centimeters is really just 0.90 meters. So I now have the radius, I have the period, I have the mass. We can calculate this now. So we got 4 pi squared. We have that radius in meters. We have that mass in kilos. And then we have that period. And don't forget your squares in the various places, because again, common mistake to forget those, and you don't want to forget those. So if we're really careful, we are going to get that the magnitude of the force of tension acting on this rubber stopper, it's about 1.6 newtons. So anything where you're dealing with tension in a horizontal circle, the only thing contributing to the centripetal force, because the only force that's in the plane of that circle, is the force of tension. That's it.